I'm a physics teacher, high school physics teacher. I've been teaching for 26 years. My background is in experimental solid-state physics, actually, and I'm going to share with you some experience I've had in the last few years involving radio astronomy. This talk was originally open source radio telescopes by Richard Prestage, but he was unable to make it, so he asked that I step in for him. So I apologize if some of this stuff isn't quite appropriate or isn't quite catered to the crowd. I'm new to the whole new radio community, and I find it very exciting, so I'm glad to be here. So I thought I should spend a minute at least talking a little bit about open source radio telescopes that Richard was going to sort of expose you to and promote. And I'll be honest, I took this from the website, so it's not a big secret. The idea here is to have a resource for those interested to share ideas and on radio astronomy, building radio telescopes, and there's a pretty big range. Idea would be to get a pretty big range of interest here, and so this site has a wiki and it has forums and so on, and I think it's sort of Richard's trying to get it going, and some of the stuff I'll be presenting about today will eventually make it there. So you can see some of the resources involved, this large-scale home-built telescope, Canadian Center for Experimental Research, and so on. I'm actually going to be speaking about the digital signal processing in radio astronomy. And so I spent the last 2 summers as a teacher involved in this research experience for teachers, and specifically this is the digital signal processing radio astronomy program that was out of West Virginia University, where we spent 4 weeks there, and then I just did something. Oh, no, I didn't. And then we went to spend 2 weeks at the Green Bank Observatory in West Virginia, testing the telescopes we built and so on. So this, you can see, is a Horn telescope, and I actually brought it with me because I bring it wherever I go. You never know when the opportunity for good radio astronomy will present itself. So actually, this is a little bit of a smaller version, and I'll talk more about it because I couldn't fit the full version in my suitcase. Whoa. So anyway, as I said, I'm John Makis. I'm from North Carolina, and I'll be presenting about this. So this is an example, of some of the telescopes that we built, and you can actually make an array if you want. I'll talk a little bit about that. So the telescopes that we built were designed to detect neutral hydrogen from the galaxy, and so it's a 21 centimeter wavelength, 1420.4 megahertz that these were designed for. And the design is very simple. It's this horn here is the waveguide, and it's this foam insulation board you can get at the Home Depot or Lowe's or whatever. And the antenna and waveguide inside are a paint thinner can and a wire with a feed through. And then you can construct a variety of frames here, depending on your desires. Now, this program is designed for teachers, and part of what we're trying to do, and I know Richard's trying to do, is to get students involved in new radio astronomy, just this whole field of technology at a younger age. And as our previous speaker mentioned, the math can be intimidating. Students are turned off by math, but I think if you can get them interested from a hands-on point of view, then that can really help. And so that's the idea here. We, as teachers are going to try to learn how to build these things, learn how to operate them, and then expose students to them at the high school or even younger level. And these devices here are currently being used by graduate students and undergrads in West Virginia anyway to do some research. So there's a lot of capability here, but it looks kind of, thrown together and kind of cheap. Well, that's the point. Teachers don't have a lot of money. We're not funded by grants from universities and stuff. So the idea is to be able to afford to build this and do some basic good science with it. So this stand here, really all the materials here cost under $50 to build. The expensive part is the LNA and the new radio, depending on which dongle you buy or whatever. So here's looking down, and you can see there's an antenna in there, obviously. Okay, so the LNA I have right here in my pocket. It was designed, I think, by Kevin Bandera at West Virginia University. And it's designed to operate the 1420 megahertz. And it's also designed to have a stable, to be stable in an urban environment. So building a really sensitive or high gain amplifier would be nice. But we want to operate these in cities where we have our schools, and so if you don't want it to be unstable. Okay, so anyway, and then we just use the new radio SDR So anyway, I'll describe the new radio program. We have our our source. We have a polyphase filter bank that then goes to a FFT or low pass filter FFT, and then the output is what I was really going to spend a few minutes talking about. So as I said, if you want to make this usable to teachers, then it has to be. These are people who aren't electrical engineers. They don't. I mean, some do, but if you want to get it out there, we want people to be able to use it, and to be able to use it, it has to be convenient. And so 2 summers ago, I did this program, and we had our new radio program output to a HDF5 file, which involved, to kind of analyze the data, it involved a little bit more than what most teachers are willing to put into it. And quite honestly, I got a little frustrated. So when I returned to this program this past summer, my goal was to try to build the spectrometer to be able to export data easily and quickly, and that can be used quickly. So I built a block in New Radio that enables us to calibrate the telescope while we're taking data, and then it displays the data with the calibration if we so choose. And then I can just simply export it to a text file that I can open in Excel very quickly. This is the kind of thing teachers want to be able to do. And so it worked. I was really excited because I had to dive into the whole new radio thing and do some programming and all that stuff. And I don't do that. I don't have a background in that, but I learned, and it was a lot of fun. And I'm kind of glad to be here because this is the kind of nerdy stuff I like to do. But anyway, when you have purpose, it happens. So I was able to build this block. We now have a spectrometer that you can calibrate the telescope on the fly. You can recalibrate it if you ever want to, and you can then just display the raw spectrum that we are interested in, which is the signal from the hydrogen in the galaxy. So there's my Horn calibration formulas, and basically we want to identify the gain and system temperature that we can then factor out on the fly and get some data that you can just immediately export to a file and open it. Okay? So anyway, the spectra, one of the also the reasons that you can actually do a lot of good astronomy without calibrating the signal, but I think students can get distracted by that background that you have from the spectrum and from the system. So that was another reason I wanted to do this. So anyway, the more exciting thing is, because you all know how new radio works and all that fun stuff, the real exciting thing is what can we actually do with these things? And I've been taking students up to Green Bank Observatory for close to 15 years now, every year. And these are students who are not astronomy students, they're physics students, but we spend 3 or 4 days up there learning how to use a 40-foot dish telescope. You can select what you want to do. This is the raw display. Down here is system temperature and gain. And once you've done that, it subtracts out the system temperature and or the system effects. You can see the temperature here is about 75 Kelvin. This is the gain. That's function frequency. And this goes from 1414 to 1424 megahertz. And so this peak here is the hydrogen peak, 1420. 0.4 plus or minus depending on the Doppler shift. And that's an interesting feature of this whole thing. So I can see it, but you all can't, so I'll just hold it up. It just doesn't like that. So let me just tell you what we can do with these things. First and foremost, we can have these pointing at different locations in the sky, and you can map out hydrogen in the galaxy. You can just, there we are, map. Okay, so we can just point it somewhere, let the sky go over for 24 hours, change the angle, do that, and you can actually map the sky that way. Or you can get a bunch of these and have them simultaneously collecting data if you don't want to do it over a week or something like that. Or you can kind of move it around. But in any event, you can map out where hydrogen is in the galaxy. I don't know if I want to use that thing. So this is galactic coordinates here. Anyway, the other thing you can do, or another thing you can do, is we can do a spectral run. So this is 1419 to 1422, and you can see the unshifted hydrogen, but this is a slightly shifted peak, and there's actually a second peak here. So you can measure Doppler shift knowing what galactic coordinates you're on. This is a galactic longitude of 53 degrees, pretty much looking in the plane of the galaxy. And by changing the galactic longitude, you can actually measure the motion of the galaxy. You can deduce, first of all, that there's rotation, and you can also figure out what the velocity is. So this is a velocity curve of the galaxy. So this is velocity here, and this is distance from the center of the galaxy. And again, this is done with these. So students can do this, and once they kind of know how to use, how to point the telescope, but that's what stellarium was invented for, thank goodness. And so what's neat about this is this totally is not what you'd expect from the Keplerian, Newtonian type behavior, where you'd expect it to more go down like that as you go out as a function of distance. And so with the telescopes, you can get students. Now I use this with my AP Physics students, and they can deduce, basically, our first observation will be just sort of pointing it at different places in the galactic plane, not doing a whole map, but just knowing where we're pointing, we can figure out that number one, the galaxy does rotate. Okay, this is high school students, so it's pretty amazing. And then we can use sort of a tangent method to figure out the fastest moving peaks in a given direction, and then map that out as a function of radius, and we get this kind of thing. And this sort of agrees with what was done by the Green Bank Observatory back in the, I think, late 60s. And they deduced the idea that there has to be the existence of dark matter. So what's amazing is that with this telescope in my school, my students are able to take measurements and actually, with some guidance, be able to deduce that the Keplerian model doesn't work, and there's got to be something else going on, okay? And that's how they figured out that dark matter is making up a good bit of our galaxy. So what can you do with these besides mapping the galaxy or measuring velocity curves or whatever? You can make an interferometer out of it, and Dr. Bandura at West Virginia had a couple grad students, or a couple undergrads actually. They did some interferometry and actually demonstrated that it could work. They also spent several weeks, or the summer pretty much, trying to detect a pulsar. I'm not sure what the results are yet of that. But we're pretty confident it can be done. There's some simulations that were done, and I think these will be able to detect pulsars. Okay, and then another possibility that those in charge are interested in is maybe using these to detect fast radio bursts. And one of the ideas is if we can kind of spread the word and get enough people from around the country with these things, that, our goal is one of these in every backyard, then we could do things with them. But one of them would be, okay, we detect that a fast radio burst happened, and can we kind of assimilate that across these telescopes and learn about them? I think there's other things you can do just with students that aren't so high-techy. For instance, when I first take these things and have my students looking at the computer screen and seeing a spectrum, they have no idea what it is. And I ask them, okay, let's brainstorm. Where do you think this is coming from? And a lot of them think it's coming from cell phones or radio towers or planes or something. So by pointing it around and maybe going out at different times of the day or different days of the week or something, you can sort of convince them that these signals are not terrestrial, because they're too regular for it to be like a plane or a cell phone or something. And then one of the other things is that if you point it in different directions in the sky, there's going to be lots of hydrogen or not so much. And so when there's hydrogen, you get a peak, and when there's not, it's a very small peak or gone. And sometimes, coincidentally, the sun might be there or something like that. So they will think, oh, well, maybe it's coming from the sun, which is perfectly understandable. So it's like, well, now once we've sort of exposed them to this, let's look at the sun. What kind of radio signals does the sun do? Okay, so you can not only run these in spectral mode, but you can run them in continuum mode too, and basically just collect the whole 10 megahertz from 1414 to 1424, and then try to learn different things about that. I actually took about 3.5 hours of data with my telescope during the eclipse, and I still have, it's a humongous file, and I'm not an expert at Python yet, so I haven't really analyze it. Maybe somebody can help me with that this week, because it's over a year old, and I'd love to just see what it's like. It's not going to be anything spectacular, but it'd still be kind of cool. It's just a humongous, and I wasn't able to adjust the integration time because I was too nervous about running this thing. So I had a 1-second integration time for 3.5 hours. So it's just this over 4096 channels. It's just this huge file. Anyway. So we can do this in the classroom, and there's different things you can do. I mean, engineering, there's a whole, the thing about these things I've realized is these things are pretty complicated. Like, my background is in physics, and so it's like, I loved learning all this stuff when I first did it at West Virginia. But there were a lot of teachers there, and it was really intimidating. I'm like, yeah, this is complicated stuff. So not only is it for the teachers for the students that we want them to get, but you have to make the teachers comfortable too. And that's going to require some kind of programs to train or to get them familiar with this kind of stuff. And on Friday morning, there'll be a forum to talk about how to sort of get new radio into education and maybe some ideas. And hopefully some of you all will come to that. Oh, and by the way, since I'm talking about that, Richard Prestige has 8 of kits. If you want to build one of these, the kit includes the CAN and the feed-through, an LNA, and a cable, okay, to go to the new radio dongle. okay, then you're on your own for the rest. But there's a whole lot of GitHub stuff out there for these programs, and there's a whole, you can get all this, you can get my, that spectrometer program and everything that's out there. So, but you'd have to go to Home Depot and buy the wood and the foam board and build your own horn. But hey, I'm sure you can do that. So if anyone's interested in that, please come talk to me, and I'll be happy to talk to you about that. But anyway, like I was saying, the technology involved in this is anywhere from building the frames. I mean, there's a whole engineering thing involved in that. And kids in high school, some of them might be interested in wood shop or building these things, and how can we make a rotatable stand and all that kind of stuff. From that to the electronics involved, to the programming, maybe some kid wants to do some Python programming or C+ programming with the GNU radio or whatever. And that's just the engineering aspect of it. And then, of course, there's the whole astronomy piece to it, which is what this is designed for. So let's see, that's a boring slide about standards. And then, so the bottom line is we want to try to, these things can do a lot. And I mean, to me, the way to learn, for students to learn, is to do it. And that's one reason I really latched on to this. I'm like, yeah, the best way to do physics, let's do some physics. Let's get these things, let's start looking at stuff, and let's see let's make sense of it rather than just pure textbooky type stuff. And so, so far I've had a pretty good response. I think my students do find it interesting, although it's a little bit mysterious. And so I just want to acknowledge some of the persons involved in this whole thing. Kevin Bandura, Richard, Sue Ann Heatherly. These are the people who are involved in the grant for the Despira RET that I've been involved in for the past few summers. And then Green Bank Observatory, of course, West Virginia, NSF. I think, yeah. All right, well, thank you for inviting me and letting me share some of the stuff I've been experiencing. I don't know if I'm out of time or...
It's hard to say at this point since we...
Yeah.
It's all right.
So.
Okay, let's thank our speaker. All right, yeah, let's have some questions. And we're actually going to pull the AM break up here and do that now and try to get an AV system that's stable. Yeah.
Oh, one last thing. Since I've built this and have this all ready to go, I do intend to take this out somewhere and see if I can detect some hydrogen with this shortened version. The real version's about twice as big, and it's funny because the real version was designed to fit through a doorway. So the question is, well, if we made it smaller, can we still get, so I'm thinking, well, it's worth a try. I mean, I'm not sure if I'll get anything, but I'm going to give it a shot, maybe at lunch or something. So if anyone's interested, come find me. I'll be happy to try to do it with y'all.
You have some. Can I ask my question first?
Yeah. Sorry. I didn't realize we had time for questions.
Oh, yeah. Good.
Uh-oh.
No, they're good questions. So, first of all, I loved your talk, and I love all of this open source radio telescopes, and I think it's amazing. And so, there's a NSF-funded program around this, right? That's going on, and I was wondering if you could just say a word or two on that, where because you know more about it than I do, where teachers like you can teach students about radio astronomy.
Right.
I was hoping you might be able to just enlighten us a
So
little.
are you talking about the RT Despira program?
Yeah. Well,
Yeah.
I think that's the one. That's what I'm not sure about. So.
That's the one I've been involved
Okay.
in. I don't know if there's other ones out there. The one I'm doing is I think up to 10 teachers per summer at West Virginia University. If they want, they apply, and there's a good chance they'll get in. And it's going on for this next summer, and then I don't know what's happening after that, but I know there's at least one more summer's worth of that. And it's for high school teachers, really from anywhere. I'm from North Carolina. This is happening in West Virginia. I think originally they were trying to focus on more West Virginia, but we've had people from Texas and California and Rhode Island. So, but it's basically to get teachers. We learn about, so we spent some time learning about digital signal processing and astronomy and all that, and then we built these telescopes, tested them, learned new radio, enough to operate this thing. And then we spent a couple weeks building or developing some curriculum. And I should say all these materials are going to be put somewhere publicly, so if teachers are interested, they can access it and all. And the goal would be, how can we get teachers who don't go to this thing, how can we get them to feel confident enough to actually you do this? And I don't know where this is headed. Hopefully it'll continue on after next summer. And I don't know if there's other programs or not.
I just wanted to let you, have the chance to mention that you're not only making like these kits and everything, but you also went the extra mile and got like grants from the NSF and then started rolling this out to teachers and schools all over the US. And I think that's just amazing. And then it's all in the spirit of open source. And I'm just baffled by the potential reach that your program might have.
Yeah, I mean, this is why I'm involved with it. I'm just totally flabbergasted. I'm like, are you kidding me? I can take one of these things and measure the galaxy with my students. We don't have to go up to Green Bank. We still will, but we can essentially do a lot like what the 40-foot that we use up there. It's not going to be the same as the Green Bank telescope, but it's close enough. A good start for students. So, well, thank you.
Can I ask another one? Okay. So I have another question. So both you and Juha said students are always scared of the math. Like how do we get students over that hump? Because most of the math is actually not that hard. And I see, one thing I see is, people's personal blogs where they will say, oh my God, math, there's no way I'm touching that, but I'm happy to learn an entire new programming language that is, I don't know, functional instead. Well, clearly one is easier than the other, but people seem to just have this natural fear of math.
I'm convinced that the skills involved in Fortnite are way beyond the math that they would need to learn to do most of it. But they're going to learn it because. So that's a really tough question because that's more of a societal question, and it happens. They've found, I think, in middle school is when the interest for math drops. 4th graders love math. 8th graders hate it. What's going on? And this is a question. And so I teach physics. We actually teach physics to our 9th graders. We do a physics first modeling instruction method at my school. And we do basic algebra. It's basically linear graphs. That's 90% of the math we do. But when you start getting kids to try to do these, 14, 15-year-olds to try to do this, some of them, the mindset, so how do you get rid of that mindset? And that's a really tough question. I wish I knew the answer. Because I agree, when I did we did the digital signal processing class at West Virginia University. We basically had a semester class in 4 weeks. I loved every minute of it, but most of the teachers there, they were good sports about it, but they felt very uncomfortable. And it's like, okay, how can we get over that? And I don't know, I think computers can be a way to help with that anyway. It's hard to say. It's a tough question.
All right, just 2 more questions, Raphael and then Moritz.
Okay, so is the LNA readily available? And do you have any good materials on sort of this dark matter inference that you're able to do with these measurements?
Okay, your first question was
the LNA, because it seems like
included in that kit.
But is it if you're going to expand this beyond people that didn't attend the course or is unable to get the LNA from you, how can they purchase? Because it seems everything else is easy to purchase.
No, I understand. I think Kevin Bandura, he's the one who basically designed and has these built. I think if we have anyone who's interested, they can contact me or him, and we can get them. That's my understanding. Is that they are available now. I don't know what he would charge or what. It's like $30-ish, so it's not like an exorbitant amount of money. If you were to buy or build it on your own, because it's not he can get these made, then it's a little bit more. But
And then for the dark matter stuff, is that going to be readily available to people to sort of understand why the measurements actually indicate the existence of dark matter? Because that seems like a very complicated thing. I don't know.
it is a very complicated thing. So what I intend to do with my students is have them, when we do gravity and we do basically Newton's law with gravity and the orbits, they should be able to recognize that the farther away you are from the center, say of the sun, then the speed drops off. I mean, it drops off like that. But we're finding it does that. So there's something not right. That's really kind of the extent of it. Now, I've thought about having my students model this because they're a little more advanced as a calculus base, and maybe do some simple models and say, well, let's try this model, let's try this model. And if you really wanted to, like if you had college students or something, maybe advanced students, you can actually figure out how much mass would give the known curve and then show that it's like 80% short or whatever the number is. And then you just sort of conclude, okay, there's got to be something more.
Yeah, that's really cool stuff. Thank you.
Yeah.
All right, last question over here.
Yeah, first of all, great talk.
Thank you.
Going back to the beginning of your talk, there's one thing that struck me when you said you're not sure if this is like the right place, and I was wondering if we as a community can do something to make people like you feel more welcome, because this is really important
No,
stuff
I
you're
felt
doing.
very welcome from the first people I met here. It's just, it was a whole black box. I was invited to come, and I had given a presentation. Part of this is sort of a two talks kind of put together. I gave at the American Association of Physics Teachers, and it was a whole different atmosphere. Very formal and very like zillions of rooms and all. And then also I found out I'm going to be like talking in front of this whole place. I'm like, oh, okay. But no, I'm just sort of kidding. I'm new to this community, but I found it very welcoming. And I'm part of my goal, the reason I'm involved in this, and I think Richard asked me to come to this whole thing, is to contribute on Friday. How can we get this out? But yeah, I'm way on top of let's try to get students wanting to learn new radio, and how can we do that? So anyway, I hope that's
Yeah, thanks.
yeah.
All right, thank you very much.
All right. Thank you.